Hello, I'm Mr. Rose, and today we're going to be discussing some banked turns. Now, I know what you're thinking. What's going on with this blurred mess behind me? Well, that is to build some excitement for physics. You can see this free body diagram. So what do we have? We're going to examine two different scenarios today, one from a classic physics example. In other words, I've got a car traveling around a banked turn, and here you're going to have a free body diagram, and we'll explain that diagram momentarily. We know from an actual technical physics standpoint that the only forces at work here are those done by the road, which is the road, the surface which the car is on. And then any reference to people that don't know physics, like that centrifugal force, centrifugal force, we know that's not really a thing. Us as physicists, we like to point and laugh and then try and help those people along. We're going to examine this from those two different perspectives. The first, the actual physics perspective. So here's my free body diagram. I've got a normal force I know from the road. I've got the force through gravity, which I've labeled mg. And I've labeled two frictional forces. Now, granted, there's only one frictional force, but I labeled two because right now I don't know if the car is going to want to slide up the road, if it's going too fast, or fall down the road if it's going too slow. And that depends on just, the nature of the problem. I am going to tell you, however, that for our example, the car is not slipping at all. So it is in perfect equilibrium as it goes around that turn. Therefore, we know that the net force must be zero. What does that mean? It means all the forces, the vertical forces, the horizontal forces, the component forces, etc., all have to add up to zero. The sources of all the accelerations, the weight of the car, the normal force, the road, the friction, all of that will act to either try and make the car go up or down the slope. We are going to examine, say, the car going too fast. So I had my free body diagram, and now here I have my component diagram. And in that component diagram, I broke down the force through gravity, my normal force. The frictional force I have going down the hill. Why? Because if the car is going too fast, it would want to slide up the hill. And then I broke things down so we have everything fitting on which I don't have, my traditional XY coordinate system. I have my normal force component in the Y direction, my normal force component in the X direction, and then my frictional force in the X and the Y direction, all of those components. We know when we sum all of those forces, they have to add to zero because it's not accelerating up or down the hill. And we know the only thing acting on this car is that centripetal force, and that's the force that's pointing into that circle. So let's get right to it. Let me move my chair out of the way. And I'm going to leave this up so we can try and reference it, or you can reference it if you need it. And we're going to go right to 10. So, I'm out of the screen. In the X direction, I've got my normal force in the X direction plus my frictional force in the X direction. We know that has to add to that centripetal force. That is the net force going in. I can break down, based on my diagram here, I can break down my components. The normal force is Fn sine theta. The X component of the frictional force is Ff cosine theta equals that centripetal force. That's everything going on in my X direction, nice and simple. My Y direction, I've got the normal in the Y. I'm going to subtract the frictional force in the Y. mg, that is also in my traditional Y component here. I'm subtracting that out. Notice all my negative signs. We know that equals zero because there is no acceleration up and down. I break into components. My normal force cosine theta minus frictional force sine theta. mg is already in my Y component equals zero. I'm all set in the Y component. I'm all set in the X component. The only thing I have left is friction. Well, I know friction is mu times the normal force. And now I get to start having some fun. Once I start having some fun, right, I can sub in I started to simplify based on my own diagrams. I like to use N. My normal force I can factor out, a normal and a normal. Normal force factored out, normal sine theta plus mu N, again, that's just going to be a mu, cosine theta, equals that centripetal force, and that Ff was subbing in for my frictional force. I know my centripetal force, by definition, is some mv squared over r. So now I have something nice and simple in one direction, that's the horizontal or my X direction. Normal sine theta plus mu cosine theta equals mv squared over r. Now in my other direction, my up and down or my Y direction, same thing, normal cosine theta. I subbed in for friction. mu times the normal force. Sine theta minus mg equals 0. Since it's equal to 0, I know I can bring that to the other side. I can factor out my normal force, so all of that, normal cosine theta minus mu sine theta, just equals mg. And now I have two equations with two unknowns. We know there are lots of things to do. What I chose to do here is divide the two. So I was dividing one component, my x component over my y component, n sine theta plus mu cosine theta, divided by n cosine theta minus mu sine theta. And then I'm dividing, obviously, the other side of the equations. What you do to one side, I have to do to the other side. mv squared over r divided by mg. We can start seeing we can lose some m's. I'm going to come over here now. So I'll lose my m's. V squared divided by rg equals sine theta plus mu cosine theta over cosine theta minus mu sine theta. So we started, if the car was going too fast, I know I went very quickly through this, but if the car was going too fast, based on my simple diagram, my component diagrams, I know that the optimal speed, so it does not slide up and down the road, has to be r times g, the radius, times the acceleration of gravity, that's the radius of the curve, sine theta mu cosine theta, adding, divided by cosine theta minus mu sine theta. You can go through this exact same process. In fact, I recommend it to derive the same equation if it's going too slow. If it's going too slow, instead of friction pointing down, the car will be wanting to slide down. Friction is what's going to hold it up. So if it's going too slow, it would just be the opposite. V squared would be r, radius times gravity, times sine theta minus mu cosine theta, they're flipped, divided by cosine theta plus mu sine theta. So too fast and too slow. That is one aspect. That is the aspect from the physicist standpoint. So now we got to get serious. What if I didn't change my diagram? What if it's not from the physicist standpoint? What if I'm looking at it from the standpoint of the driver of the car? I'm not a physicist. I pretend to be a physicist, especially on YouTube. But what if it's from the driver of the car? The driver and the car have to be just as valid of a reference frame as the stationary road. Any force that I feel as I'm driving the car has to be treated as a real force. I guess it doesn't have to be, but can be treated as a real force. So from my perspective in the car, I've got this free body diagram. Again, we didn't know what we were going to do here, so friction is going either up or down the road, depending. I know I've got some weight or some mass to gravity, and I know when I take that curve, I feel that force. That FC, not a physicist for this problem, that FC is what I'm going to define as the centrifugal force, not the centripetal force. So since the car, again, isn't going to slip, we're going to say that, the net force, thus the acceleration, all of that has to be 0. This means that all the forces parallel to the surface of the road must be 0. The sources of all of the acceleration are the weight of the car and the centrifugal or the centrifugal force it feels. So to deal with all that, I have to break all of this back into components. Now this is going to be components from my perspective inside the car, these things that I feel. My centrifugal force has a perpendicular and parallel component. My weight has a perpendicular and parallel component. And friction is parallel to the surface. Again, I'm going to say I'm going too fast, so the friction is pointing down. That means the car wants to go back up the road. So how does this play out? Yeah, I got nowhere to put this. I'm going to slide this around as we go, keeping the diagram up for reference. So start it. My parallel component of that centrifugal force minus my parallel component of gravity minus friction, one going the opposite direction, has to equal 0. We know that. Break it into components. FC cosine theta, that's easy for my diagram. mg sine theta, easy for my diagram. FF doesn't need a component. It is perfect in that what would be the skewed axis, again, I left that axis off, has to be equal to 0. We know FF equals mu Fn, so for not a physicist driving a car, we're pretty smart. We know that. FF equals mu, FC perpendicular, plus mg perpendicular. Again, from my diagram, all of that has to equal out. Now I can start subbing in what I know FC parallel, FC perpendicular and mg perpendicular are, mu is still just my constant, FC sine theta from my diagram, plus mg cosine theta, also from my diagram. Now the real fun starts. My parallel components here, let me get on this side. My parallel components, FC cosine theta minus mg sine theta, minus mu FC sine theta plus mg cosine theta. I pulled that, pulling that directly from what we have here. And now I can combine some terms. I want everything with a mu on one side, everything with an mg on the other side. The color coding hopefully helps. I pull out my FC, cosine theta minus mu sine theta, minus mg sine theta plus mu cosine theta. All that has to equal 0. And now we know that this centrifugal force, from my perspective, from the observer, is that mv squared over r. Throw that back into my FC. mv squared over r, cosine theta minus mu sine theta, minus mg sine theta, mu cosine theta, nothing changed, equals 0. I can drop an m, right? Let's see, can I drop an m? I drop an m. Yeah, I can drop an m. V squared over r equals all that same stuff without my m. Since it equals 0, I can bring this whole term to that side. V squared over r, cosine theta minus mu sine theta stays on this side. G sine theta plus mu cosine theta goes to the other side. I can bring that r to the other side. I can divide cosine theta minus mu sine theta. And I get the velocity if I'm going too fast. The friction to keep me there, what that velocity would be, the radius of the curve times gravity, sine theta plus mu cosine theta over cosine theta minus mu sine theta. So we can see it is very different from, it is not very different. Physics is physics. If I believe that centrifugal force is real, and I can break things down correctly into the components, it gets more complicated. But it doesn't mean it doesn't work. Anything that I observe, I'm observing a force, I should be able to calculate that force. And that's the purpose of this exercise. V squared equals rg sine theta plus mg cosine theta over cosine theta minus mu sine theta. Has to be the same. Centripetal acceleration or the observation of centrifugal force. I also invite you to do the same thing we did earlier. In fact, I suggest it. Try and calculate it if you're going too slow. Rg sine theta, mu cosine theta, subtracting the 2, over cosine theta plus mu sine theta. This would be too slow. Furthermore, you can take these terms and you can find a maximum and minimum velocities. I recommend you also try and do that. That's all I have today. Hopefully my edits work. This is the first time I'm trying this edit thing, so if you have a comment, by all means, comment. And as I have been corrected, like, click, or subscribe doesn't mean anything. It's supposed to say like, comment, or subscribe if you're watching this on YouTube. So hopefully you are. I take all feedback. And thanks. That's all I have for you, and I'll see you next time.